Let's go ahead and get started. Just a couple of quick administrative notes before we continue on with the social engineering topic. You can see where we are on the calendar. I already posted an announcement about it, but just to make perfectly clear, we're in week 10. This is checkpoint number 2. This Thursday is MQ Bravo. Just like MQ Alpha sort of covered the first 4 topics, MQ Bravo is covering the next 4 topics that we have covered. Just to make that perfectly clear, that's lecture 5 material, 6, 7, and then I would guess the first half of 8, where we left off last Thursday. So it lined up pretty well. The things we covered today are relevant, but there's no questions specifically about it on Thursday's test. I reviewed the questions just to make sure everything was kind of in alignment, and I'm a little hesitant to say this, but I think it's easier than MQ Alpha. It's easy for me to say. I looked at the questions. I got 100%, so I know the material well enough for that. What it is slightly less hyper-technical, right? There was a couple of multiple choice questions on MQ Alpha that if you didn't know the specific port number, you got the question wrong. And there's nothing of that particular flavor where if you didn't memorize a specific factoid, you would have trouble getting it correct. There's nothing of that nature. But it's been a busy 4 weeks or 5 weeks since the last one, right? So you should take a little bit of time between now and Thursday and review. You can review the videos. You can just look at the slides if you don't want to look at the videos. There is the corresponding reading, and you don't, I think, need to look at both book 1 and book 2. As I mentioned earlier, they're written in kind of a different style, even though they're covering the same technical content. Pick whichever one you prefer to read through, the more casual or the more sort of traditional textbook style. And I would recommend just reading through that. And I do believe that if you do that, you're going to be very happy on Thursday with your results. First test went fine. This one will also go perfectly fine. There's a few questions on authentication. There's a couple questions on web applications, 1 or 2 questions on physical security, and then there's a couple social engineering questions. So we have 25 minutes allocated for it. I do think that's going to be plenty of time. You're not going to be sitting there staring at it, not knowing what to put for a particular question. But you do need to be here. So I'm preaching to the choir. Those who are here currently, you've been attending class on a regular basis, but expected that people will be here in class on Thursday to take that test. Otherwise, we're really getting into the home stretch of this semester. Oh, yeah, sure. Question. Absolutely. Yeah. Yes. There is mostly multiple choice. There is a couple of fill-in-the-blank style questions. I don't want to say what the question is, other than it has to do with authentication and hash function, and I think it's fair. So I looked at it again, and then there was a short answer question. So you won't get your entire score back instantly because I have to go in and manually grade the short answer question. Looking back at our schedule, we're moving on to Lab 9 this week. The TAs haven't had copious amount of free time to kind of beta test the lab, and as I was deploying things for Lab 9, I'm seeing some weird warnings and errors I don't normally see. So have a little bit of extra grace this week. If things don't look perfectly right in lab, I think we can figure out what possibly went wrong because there was quite a bit of deployment specifically for Lab 9 that we didn't have to do for the prior labs. For various not terribly interesting reasons, we take some machines offline, we bring some other machines online, specifically for lab number 9 to kind of keep it self-contained. So this week in lab, work with your TA, try to figure out if something's not working, we can troubleshoot and resolve as needed. Otherwise, I really do want you to look at the schedule and realize, where we are in terms of the semester. We're really going to jump into that home stretch here. Before you know, it'll be Thanksgiving break. We can keep meeting if you want over break. There's no requirement we don't have class. It just can't be mandatory. So we can take a poll, and if you just want to come back on Tuesday and Thursday at Thanksgiving break, we certainly can. Otherwise, we're getting to the point where I'm not going to say optional topics, but we will have pretty much covered everything we absolutely are required to. So hopefully the class still remains enjoyable, reasonably so, but you're really in that home stretch. You are going to see a definite sort of change in tone in what is happening in lab. Lab 9, it's got some interesting things to it, but it's another lab of that nature. Lab 10 is also of a similar nature. And then for our quote-unquote final project, there's no longer that exact sort of hand-holding of now type in this command, now type in this command. Some of you are going to find that project very straightforward. It's a matter of reviewing back prior lab-related notes, determining how we accomplish certain things throughout the semester, and essentially sort of repeating those kind of tasks with some slight variance here and there, applying what you've learned versus just following particular instructions. If you've just been kind of blindly, type, 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 copy, paste, copy, paste, copy, paste, you're going to find that a bit of a step up in difficulty, as it just tells you what you need to accomplish, not exactly how to do it. But we're also there for you as well. So, formulate good questions, reach out when you need help, and you'll be fine on those labs as well. But that's really the remainder of the semester. So this Thursday, MQ Bravo, then we really jump into that home stretch. And my opinion is we're all doing extremely well this semester. So you should feel good about where we are. Yep.
For the final lab, do we need to go to each of the lab periods that we would normally go to, or do we have to go to the first one and then we can go to the lab after that?
I could talk about that with the TAs. We've been a little lax. Historically, the policy of this class is if you aren't physically in the lab, you get no credit for anything, and I haven't been quite so strict. Definitely come to the first week in lab. What it is a guaranteed couple of hours where the TAs will be there and your fellow students, and you can always talk through ideas. There's enough things to do that it will take you more than just the 2 hours to get done for both of those parts of the lab. Whether I will manually do a check-in of you on that second week, it's not part of the rubric. So if you're done, you're done, and that's fine as well. We were talking about social engineering and a little bit more of sort of the technical side of social engineering, right? There's the human element, which is critical, but part of what are the various ways in which technology can be used to trick users into doing something that they weren't necessarily intending to do. And where we left off on Thursday was talking a bit more about homoglyphs. You also hear the term homographs. It's really a similar concept. Homo meaning same, glyph meaning character, or graph meaning word. So it's either a character we're kind of tricking you into thinking something else, or an entire word, but technology-wise, it's exactly the same concept. There's kind of the old school homoglyphs of google.com with zeros versus google.com with O's, Microsoft versus rmicrosoft.com, and the like. Those are very font dependent, also screen resolution dependent, and so while looking at it at a big screen here, we may say, well, I would never fall for those examples. It really depends on the environment, who is using the computer. If they're in a rush and trying to do 15 things at once, there is still some potential for fooling people. That is with I would call the traditional ASCII homoglyphs, or just characters in the ASCII table that look something like other characters. That is a relatively small number of characters, right? We talk about ASCII being this 8-bit encoding, 100 some odd printable characters at most, versus Unicode, which has up to a 32-bit space and millions of potential characters that are available there, for which it turns out, for all sorts of interesting sort of historical reasons, there are all sorts of characters in other languages and corresponding language sets in the Unicode table, or the Unicode encoding, that look, I think to the human eye, effectively identical to well-known, more typically used characters in what we would call the Latin encoding here. So when I say iastate.edu versus iastate.edu, you can copy paste that. One of those is encoded with the Cyrillic A, one is encoded with the Latin, the regular A, whatever you want to call it, and you can't visually, I believe, see the difference. And even when overlaid on top of each other, there is technically a difference there, but it's extremely subtle and not one that some user could be expected to visually disambiguate. And it just turns out there's a number of characters that fall into that kind of Venn diagram of looking like characters that are actually different in other character sets here. It's long been recognized as a big phishing risk. There's a current solution used by all major web browsers. I would argue that it's only a partial solution, and we can talk about why I consider it just a partial solution. So the current solution is we do allow that in terms of using Unicode to encode a domain name. We can do the iastate.edu with a Cyrillic small letter A versus a Latin, a traditional small letter A here. In fact, if the entire domain name is using a particular, we'll call it subset of the Unicode encoding, or a specific language or specific part of it or alphabet of it, if you're consistently using Cyrillic in the domain name, that's allowed just by default. Or if you're consistently just using Latin characters or ASCII characters in the domain name, that's also allowed, without any required re-encoding or warning that that is the case here. I don't have an example here, but if the domain was entirely in Cyrillic, that is just allowed without any modification of the domain name. Only when there is some intermixing of character sets, now the default assumption is that is a sufficiently large phishing risk that by default we now re-encode those. Again, it's not because it's just using Unicode, but because it's using a combination of Unicode characters that are falling between different encodings, different character sets. Those then get, I use the term render here. I could also call it sort of re-encoded as what's referred to as puny code here. And we'll talk a little bit, but not that much about the algorithm, but what winds up happening is for those characters that are in the alternate character set, those get effectively removed and re-encoded at the end of the domain name. That is only a partial solution, right? If I were to go to, we'll talk about the encoding for Zambrino.com, tremendous website if I say so myself, and instead I have the A in Zambrino.com. Well, in this case, it's probably going to be a sufficient solution. What will happen here is that that's just copy pasted from that slide, I press enter in my sort of URL editing bar here in Google Chrome, and that exact kind of re-encoding happens. In this case, I don't know how well you can see that. I'm actually not going to be able to make that larger. It's quite visible on the recording. It's the XN dash dash with the A getting removed. We'll talk about it more in just a second here. In this case, you could argue, well, success. You have taken what was meant to be some misleading URL and you've then re-encoded it. And in this case, there turns out to not be anything at that particular domain. There is no Cyrillic Zambrino.com. Maybe there should be. This is an opportunity for you all. But because there isn't, well, I guess we've succeeded. We've re-encoded it. No one's accidentally gone to a website that turns out to be something else. But there could have been. I mean, this example doesn't happen to have a phishing website located at that URL, and so it just goes to a page not can be found page here. If there was a fake version of that same web page, the only real protection that's provided by modern web application stacks, by modern web browsers, is that re-rendering of the domain. Are you always going to be staring at which domain you actually have open? Will you be doing so on a mobile browser or some custom browser used for some other web application front end? It's not always clear. So it's a re-encoding or re-rendering of the potentially homoglyph Unicode characters here. It's still a potentially valid domain, and so the attack vector is still there. We're just putting up a little bit of a warning light saying, what you thought you typed in got re-encoded as something different. I believe it still requires a somewhat savvy, attention-paying user to detect that such a thing has happened, and it's not just business as normal. I mean, we maybe always look at the URLs that wind up getting generated, but it depends on which browser you're using in which scenario, whether or not you will always catch it. Okay, soapbox aside, the basic algorithm is relatively straightforward with a small wrinkle we won't cover in too much depth. So we start with the domain name that requires that translation. You can't see it, but that has the Cyrillic A there. We just remove those characters that are from a different Unicode language set, and we add a hyphen to the end before the .com or the actual domain itself to indicate that there's non-ASCII characters present. And then there's just a ASCII compatible encoding prefix that gets added, so that's why it shows up as XN dash dash. Don't know why it's XN dash dash, but there's some quasi-standard associated with that. And then we take the character that we actually pulled out, we still need to encode it in some way, and we use something of an arbitrary encoding scheme where we generate a number n times j plus I, where I is the index in the original domain that character was located, n is the possible number of characters it could have been located at, and then the value of j is probably the critical one. It's the actual value in the big Unicode table, the byte sequence corresponding to that particular Unicode character that needs to get inserted into the actual domain itself. So n times j plus I in this case would be a value of 1. We start with location 0. Location 1 was the entry in which we wanted to encode it here. Out of, I believe, 8 possible locations here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. I write here 9. I'm trying to remember where 9 comes from. Possible insertion points, because it may be at the very beginning and maybe the very end. That's why you wind up with 9 there. And then you multiply that by whatever that value happens to be in the Unicode table. That's just kind of an arbitrary value. That's Unicode 4430, that's 1072 in decimal. We kind of assume that we're not encoding the original ASCII set, so we subtract 127 from that. And then where it gets a little hand wavy is then that gets encoded via a system that's pretty close, but actually slightly trickier than just base 36 encoding. We've talked about a few different encodings this semester that you just need to be reasonably fluent in as someone who is a cybersecurity professional, right? We need to know, regular decimal encoding. We need to know our ASCII table, certainly. We need to be aware of Unicode. We talked about base 64 encoding previously, which is where our hash values in our password files and hash sums are getting generated as. That's the 64 printable ASCII characters that are used to encode. This encoding isn't as critical, so we won't follow the entire algorithm, but it's basically a base 36 encoding where you use A through Z, that's 26, and then 0 through 9 to get to 36 possible digits to generate from what is a larger base 10 decimal number, something that's a relatively small number of those base 36 characters. And that's what your Punycode looks like. From the user's perspective, you could basically say, I see xn minus minus xn dash dash at the beginning of my URL. Something may in fact be going on here. And this is not just a theoretical attack. This is something that has happened in the wild. And again, even if we do that Punycode encoding, and this was from an era before that was in common practice, people can still get foiled by this. So this is a pretty well-known, the BetaBot exploit delivered by a fake Adobe Flash website. So it starts with some social engineering attack versus email versus some other vector, providing a link that you must download Adobe Flash installer. In the bad old days of the web, you would install all sorts of various plugins to get the various aspects of the web to work. Installing Adobe Flash was something that was kind of expected. Perhaps you're on a new computer and you realize you think you may have to install it. Can we tell by looking at it what's wrong with that Adobe link? It's pretty hard to see on that particular screen. That's okay. There's a dot underneath the B character there, so it's not the letter B, it's B with a dot underneath it. And if you look at the slides or the video later, you can actually see that particular pixel there. What happens though is in a certain reader, whether it's an email reader or something else, that dot basically gets entirely hid because the link itself is underlined. So it's also there, but you just now really can't see it because it's got that underline that's hiding it. I actually tried to look up prior to today, what is the point of the Unicode character B with a dot underneath it? And it's actually not a standalone character. It is a regular B, and then there's a separate character that allows you to say in Unicode, take the previous or current character and put a dot underneath it. So there's no language, at least via my investigation, there's no language, whether it be technical or just a linguistic thing that requires a dot underneath a B. But it's something that, given the expressiveness and the intention to be kind of future-proof of Unicode that allows for that character to be encoded. So you can see where we're going from here, right? So you have a link that looks like adobe.com. It's actually adobe with a hard B.com, and that's going to a site that, even if one were to investigate it and kind of do a little bit more exploration of, well, is the site set up correctly? You look at the certificates for this site, it at least has some sort of self-signed certificate. You look at the registration for the website, it looks okay. Instead of San Jose, California, whether intentionally or not, it said San Jose, Mexico, but otherwise it looks effectively the same as the intended legitimate Adobe domain. And the end result was an installation of a fairly nasty piece of malware known as BetaBot. BetaBot's kind of fun. We'll talk a little bit more about malware in the next week or so. We don't necessarily have all the technical tools in this class to really appreciate the nuts and bolts of what happens in a modern piece of malware, we can look at it and get a feel for what it's trying to do. This is an example of a botnet of the type we'll be talking about a little bit later this week and into next week. What's interesting when looking at when people kind of reverse engineer and then effectively eventually publish the software for these malware sources, is kind of like any other piece of commercial software. It seems like a big chunk of the source code is actually trying to implement some version of what we refer to in other contexts as digital rights management. A big chunk of this software, and if you just kind of look through the source code of this, is actually trying to protect itself from people using it without paying for a particular usage key, like a license key associated with the software here. So all this stuff that got encoded or decoded, excuse me, and it does have that feel of kind of auto-generated source code from a decompiled binary. So it's not super human readable, and there's things like variable names that are known as unknown, unknown 2, unknown 3, and that's indication of decompiled code that someone's trying to add like manually the appropriate source code context to it and kind of failing. But a big chunk of this code is actually just a decryption routine that's given a particular key is effectively unlocking the quote unquote real software here. And so if you want to see what the actual beta bot software looks like in the wild form of it, this is taking a long time to load. It's just a big old sequence of bytes. So there's your beta bot there. So it's actually nothing at all. It's source code, but it's not, right? It's just the hexadecimal byte dump in a format that could be read by a function written in C that can take a 250K or so blob of bytes and decrypt it into its intended functionality. There have been breakdowns of this code and what it actually accomplishes. It attempts to disable antivirus, so you see a lot of strings for known antivirus vendors, so it tries to shut it down. It's just a sort of typical type of botnet otherwise that is attempting to reach out to a command and control server and wait for its next command. Oftentimes, people who are able to kind of reverse engineer and take down these botnets and sort of prevent the proliferation of these botnets, that's the part of it that they look into, which is decoding, decrypting the actual command stream that comes in to determine where to next. What is the next command going to be, under the assumption that if you can overtake that command stream, you can then take over the entire botnet yourself and you can tell it to turn itself off or to do something more innocuous. That write-up is available. You can click the link on the slide. The source code, if you just want to kind of look at what malware source looks like, that GitHub repository has a large number of malware examples on there. You may find them a little unsatisfying for the same reason that that example is not super satisfying. A lot of reverse engineered things, a lot of just byte code kind of encryption and decryption routines to kind of obfuscate and sort of protect the underlying source. And then otherwise doing some very straightforward reaching out to a web service, getting a result back type of code associated with it. This is a bit of a context switch, but I'm going to make sure I can tie it back together into the social engineering concept that we are covering here. So I want to provide a very brief, a very high-level introduction to machine learning. Just a show of hands for the 50% of you who are in class today, who here has taken a machine learning class before, Iowa State or otherwise. That's good. So here's your first introduction to it. Who here has studied it on their own, kind of outside of a classroom environment? Okay, so a couple of you. That's great. It's probably a critical field. In a couple of years, we'll almost certainly have a required class in it, even for cybersecurity engineering students, and certainly for electrical and computer and software engineering students. We're not quite there as of yet. It's a subfield of artificial intelligence, a term I think you all would have heard of. That the idea is that it's a use of special algorithms that attempt to learn from existing data and perform tasks on subsequent data. And this is a topic that could have been introduced in a class like this 30 years ago. What has really changed has been just the recent, and even last 10 years, recent advances in algorithms as well as advances in computing hardware. Machine learning has gone from an interesting kind of research niche kind of field to sort of revolutionizing, taking over a variety of different fields, including language processing, language generation, image generation, computer vision, speech processing, and data filtering. We will see why that's relevant for us in this concept of social engineering, but just give me a little bit of rope to get here. There are big top-level categories of machine ML algorithms. You'll hear the term supervised versus unsupervised learning. In both examples, you have some prior amount of data, and sometimes that's the fundamental challenge. You have this big blob of data corresponding to a particular log or task or just data set that is collated, collected for you. In supervised machine learning, that data is labeled for you, and your algorithm is then trained based on that data where it can compare the results it generates to what is sort of known pre-generated results. If you want to think of it as a big folder full of cat pictures, each of which are labeled cat, that's one way to think of what your supervised training data would look like. Versus unsupervised data where you have prior data not being labeled and you only have examples of input, and the algorithm itself has to determine how to organize what the data should correspond to. Sort of an orthogonal categorization of ML algorithms is whether it uses reinforcement learning. In this case now, it's not as simple as saying, here is data that has a label or it needs to be generated, have a label generated for it. Now it's closer to a more traditional optimization problem, which is I have some task I need to accomplish. It's not a true false kind of task, but it's more about a reward function that gets generated that gives you some sort of goodness result of a particular solution. And the goal is ideally to try to maximize how much goodness the algorithm can get back out. That is a 30,000 foot view of machine learning. Historically, and really we're talking about the last decade plus here is all that we really need to cover in terms of understanding what's been very influential in machine learning. There's been a few really kind of revolutionary ideas that came out, one of which is AlexNet. This was the first kind of well-analyzed use of what's referred to now as a deep convolutional neural network for machine vision. That is a bit of a mouthful here. You can look at the Wikipedia article for AlexNet. The guy's name was Alex. His advisor has won, the Turing Award, and he just 2 weeks ago won the Nobel Prize in physics. Convolution means basically a combining function. You can think of it like a filter. It really depends on your background, whether you come from just a programming background or have a little bit more of a statistics or signal processing background. And the idea was behind AlexNet and many, many related architectures is you can take an image as input, and even though it doesn't necessarily make intuitive sense, and it's very hard to explain why it works from base principles, and that's a whole separate sort of field of study of how to explain it, why it actually works in practice. You take an image as input, that's meant to represent that matrix as just an input image. You take a chunk of it as a time, in this case, 11 by 11 chunk, and you kind of do a sliding window where you take a chunk followed by a chunk followed by a chunk, and you apply these operations referred to as convolutions to it. You can just think of them as successive digital filters being applied to it. Multiplying it by a set of values, adding up the results together, and doing that, for want of a better word, a whole ton of times. That is a deep convolutional neural network. I have some colleagues who'd be very upset with me if they heard me describe it in that way, but from our perspective, that's kind of sufficient. Taking an image, grab a chunk of it at a time, multiply it by a bunch of values. The key part is determining what those values you multiply it by is what happens during the training process of that model. And you just keep sending images of cats at it and telling it that it's cats until it generates enough outputs that say, yes, I agree with you, this is in fact a cat. And then you determine for future images that you don't know whether or not they're cats, it gives you its best estimate as to whether it's a cat or whether it thinks it's something else. And this was a pretty revolutionary implementation at the time because it was getting orders of magnitude of like 90% accuracy of determining for well-known image benchmarks what the object was expected to be. That's one major milestone. You probably know more than me about ChatGPT and the like, but there's been other software like AlphaZero, AlphaGo Zero for computer mastery of chess and other games. DALL-E is kind of the first sort of consumer level, artistic and realistic text to image generation. In terms of the other very fundamental sort of research contribution, there was the idea of transformer models, attention models, or the transformer architecture. The concept there is that as you take your text and you break it up into individual tokens, this concept was, as opposed to just worrying about how the previous token should influence the next token. Let's look at a very large window of tokens, a context of tokens, and let's assume that anything within that window can potentially impact what should come next in that window. And you can't necessarily see that in this figure, but it realizes, hey, we have really big GPUs these days that can do a ton of processing. Let's just look at the whole paragraph at a time and use that to determine what the next word or character should be in that particular paragraph. That is what's driving all of the GPT and related models these days. We have several very good courses at Iowa State in machine learning. Depends on your background, depends on your field of study. And so this may not even be a sufficiently exhaustive list. I was thinking more from computer science and engineering perspective when I put together this list, and then realized we have students from all over the university in this class, and I'm glad you're here. This is a starting point. You have to always look at the prerequisites for the class and see if you're eligible to take any of these particular classes. Some are more kind of double-y, others are more computer science, and then we have computer engineering ones as well. Eventually, there will be a core required class for Sci-E focused machine learning. That's not today, and maybe not by the time you graduate, but soon that will be the case, and we will have such a course ourselves. That's one note I want you to consider, that this is our 15-minute version of machine learning today. It's a whole semester, multiple semesters. The other caveat or other note is this is a rapidly changing field, and we have to be very careful when we say such a thing is not possible with machine learning. There's been enough examples that even over a period of weeks and months, something that was thought to be impossible X number of weeks or months ago turns out, with a new algorithmic innovation or new data set or new generation of hardware or just more resources spent on the problem, turns out to be feasible. So it's an exciting time. It's a scaring time. You've probably seen this before. This is 2023, which is not a long time ago. Let's remember here. This is early 2023 benchmark of Will Smith eating spaghetti. It's kind of disturbing, but I love it. This is AI generated. You've certainly seen this before. No? Okay, we travel in different circles, and that's okay. That's AI attempting to generate Will Smith eating spaghetti. That's 2023. We'll just let that run to its glorious conclusion. And here's 2024 version of Will Smith eating spaghetti, also AI generated. That's just a period of months, actually really weeks later in terms of what the technology is capable of doing. Almost to the point, pretty convincing. You know, again, you have the fuzzy projector in class. Maybe you can't see it all that well. There's a couple tells. What are some tells we can see? Yes, he's not actually eating anything. Like the plate still kind of stays stable, and he's not actually eating anything in the noodles. He also changes into clearly a different person at some point during eating. But in terms of an automatic AI-generated video, there's a huge leap in terms of what the technology was capable of doing. Yeah, I didn't even notice that one, so that's excellent. So it's not an AI benchmark, but if I had my way, that would be an AI benchmark, that every new tool would attempt to generate Will Smith eating spaghetti to see how far it's come. Oftentimes today, we talk about sort of image and audio generation to worry about from the cybersecurity perspective, with video not being quite there. But again, that's the note about, okay, maybe not today. Let's check back in 2025 to see, how convincing AI-generated video of realistic people can become. Again, just like with the homoglyphs and looking at a domain name that's technically quite a little bit wrong, if you were looking at that very quickly, or if it was your grandparent looking at it, they may say, oh, what a nice video of Will Smith eating spaghetti, and not realize that it's AI. And that's today. Let's see what next year brings for that. There is a direct connection between these two topics, not just social engineering, but cybersecurity in general, right? A big part of what we do with traditional computer and network security is trying to detect outliers, right? And certainly intrusion detection systems, that is effectively the name of the game. We have this model or concept of what normal traffic should look like, and a fundamental task is to determine when something abnormal happens. Well, at least that's one approach, right? Another approach is to say, here is a set of of signatures or logs to look for that specifically we know to be an issue. Otherwise, we can take this sort of statistical approach, right? Here is where our traffic should look like and what we consider to be normal traffic. Once we see this, we know something potentially is up. Looking for outliers, detecting new threats. Well, there's a good reason to believe that machine learning, by its very kind of nature, these same kind of things that can be used to generate videos of people eating spaghetti, should also be pretty good at detecting outliers and potentially identifying new threats. Because while these algorithms do require typically large amounts of data to be trained, to be able to process and detect and generate new things, that usually isn't that big of a problem from the security perspective. We've talked a little bit about this, but our network traces, our network statistics, our packet captures, our logs, those are going to be a large amount of streaming data that could be analyzed by such a system. This is just one of many Iowa State research projects that I just brought out here. NSF-funded project that's looking at what they called continuous authentication. The idea you have some existing authentication, whether that's two-factor, whether that's a fingerprint, whether that's eyes, password, and that in addition to that one-time authentication, there's this continuous ML-driven authentication, which is monitoring your usage of a system to determine if your usage becomes an outlier. Whether that's network logs, whether that's things like even keystroke pattern detection. I guess depending on how invasive you want to be, it could determining, your eyes if the user is changing. That's meant to maybe prevent a potential, security consideration where you have someone piggybacking on a machine, or whether you're leaving a machine unlocked, or whether the authentication credentials have been lost or stolen by someone who doesn't otherwise meet the same behavior or context that's being monitoring. And then separate from that, just because of its power for computer vision, the idea of facial recognition is almost entirely switching over to these ML-based approaches. They all come across as a little bit more hackish or ad hoc when compared to traditional computer vision approaches, where there's an algorithm that's very fine-tuned to detect if something is an eye, and an algorithm that's very fine-tuned to detect if something is a nose, and it takes all those together and then it combines them and determines whether something is a face. And there's more of an engineering mindset to that sort of algorithmic design versus these type of architectures, and not even to mention, a decade plus of innovation past the initial deep convolutional networks, which is, let's just throw a lot of multiply accumulate operations at the image as it comes in and see how it correlates to previous faces that we've seen and generate a pretty decent result. But the success of those models can't really be understated in terms of how accurate and how effective they are. But they are all pretty fragile, kind of by design. I don't know if I made the point well enough here that I wouldn't say these approaches work accidentally. It's not a coincidence that they wind up working. They are trying to encode fundamental features of an incoming image to determine if something is a cat or something else. But they're fundamentally also going to be fragile. The model itself doesn't know anything. It's providing a statistical best guess based on its prior computation and storing of previous images that may look to some extent or the other similar to the current image that is coming in. So from a cybersecurity perspective, the algorithms, the implementations are quite impressive. I don't want to undersell how impressive they can be, but they do also tend to be fragile, accidentally fragile, and then specifically researchers have found they can be fragile to sort of carefully tailored, carefully targeted inputs. And the term you will see is referred to as adversarial machine learning. Now, in some contexts, this is intentional. We intentionally create adversarial inputs to kind of improve the robustness of our model. But in general, adversarial machine learning is part of a continuing arms race with both cybersecurity and ML technology. The idea being you can take an image, which to the human eye, we can determine what it is. But because these algorithms, let's go back to this picture one more time, because these algorithms are fragile in that it doesn't really know something is a cat or not. It is applying a lot of convolutions to an input, some statistical processing on top of that, and doing that with a whole bunch of pre-trained, pre-labeled data to determine whether something is a cat or not. Because of that, And because the algorithms are generally public or reasonably well understood to the public, we can then modify our images ourselves if we are an attacker or someone who's trying to break a facial recognition or image recognition system. And we can add what would look like to a human as sort of random or imperceivable noise. And we can actually get a completely different output from such systems. This is just two examples from sort of research papers. But the concept is definitely not a solved one, an addressed one in current production systems. You have an image, and this would be a typical output of a convolutional neural network. You provide this image as an input, part of some image benchmark, and it says this image is a panda, and it gives you some sort of statistical confidence that it's 57.7% confidence. And then it turns out that this may look random, but it's intentionally crafted with particular knowledge of the underlying machine learning network that's being used to make that prediction. It adds that noise to the image. Because it's just kind of some statistical noise, the end result still looks, I think, to us like the same thing. Like visually, it's, I would say, imperceivable that it's not the same exact thing. But now, because of how it was crafted, it thinks it's a gibbon with 99.3% confidence. Now, from a cybersecurity perspective, we don't have a lot of panda detection algorithms that we're necessarily worried about. But now think about autonomous driving. And what your Tesla is doing is it's driving down the street. Car. Given some small, again, seemingly trivial perturbations, you can fool those machine learning algorithms. And now it thinks that this is a cake here. Again, probably your Tesla should also stop it when it sees a cake approaching. So whether that's a big issue or not. The other example provided here is messing with stop signs, and that's been an active research project as well. This is a stop sign in which someone seemingly applied some graffiti to it, right? And it looks like kind of arbitrary. Graffiti loves, stop, hate, whatever you want to do to modify the stop sign. And it turns out, for reasons that aren't really dissimilar from this image that we've just add carefully tailored kind of randomness to it, what looks to be visually sort of random, it's not randomly selected, we can fool certain classes of algorithms that had previously detected that this would be a stop sign if it now instead detects it to be a speed limit sign instead. Now you have a real problem. Panda versus gibbon probably doesn't come up too much on a day-to-day basis. Car versus cake is kind of fun, but hopefully your car also stops for when it sees cake approaching at 50 miles an hour. Turning a stop sign into a speed limit sign is a big issue, right? Presumably that would cause accidents, that would cause all sorts of problems when that would happen, right? And that's not just for street signs and the like. There's been similar projects, kind of a combination of sort of art and science, and I think it's kind of cool, and that's why I provided a couple of links here from different groups, which have shown that with sort of carefully constructed hair, makeup, and accessories, you can actually fool face recognition as well as facial detection systems so that you can kind of go hidden from the rest of the grid. I think I have the one link open here. CV Dazzle is kind of a cool website. It was proof of concept, but the concept is still considered sufficiently robust that, again, to the human eye, these are all pretty clearly people, and via some carefully tailored, and this is more, again, art project than truly a sort of a scientific investigation here, carefully tailored hairstyle, makeup, maybe accessories, this can kind of fool facial detection systems, and they don't even detect that these people are considered to be faces. This is gonna be my look for Halloween. I don't know if you think I can pull it off. Okay. Compared to, this is more of an academic research paper where it's not trying to fool facial detection, but what it's able to do is fool facial recognition. And this may, I understand why this may seem a little bit magical to us that such a thing is possible, but these researchers were able to show for very similar reasons that these networks, while very impressive, are also quite fragile. And small changes in input can lead to large changes in output, and specifically small, very carefully tailored changes can lead to significant changes in detection output. And in this case, it's printing, 3D printing, very particular patterns of glasses and glass frames that lead to fooling facial recognition software into thinking that you're someone else entirely. So from the cybersecurity perspective, I think it's important to recognize that these systems are already in very wide-scale deployment. That's not changing anytime soon, but they're all very fragile. And that's also not being changed anytime soon as well. Similarly, if the model itself is trained on user data, that could be an inadvertent source of information leakage. And whenever someone is deploying a new GPT model and I want to try it out, I attempt to get it to leak as much information as possible. Separately from that as well, this concept of phishing, which whether it needs to be a separate word or not, but that's voice phishing, already was a thing, right? Just like we have phishing, which is sending you sort of a fake email or a fake link that you are clicking on and thinking it's a different domain or a trusted domain. You have this fake voice that is tricking you into doing some particular action. But that's becoming a more critical issue. In looking it up, deep fake audio is already illegal to use on calls as sort of a federal rule or federal policy. But I guess the thought is that the people who would be employing such a thing don't really care that they're breaking law. That it's already their goal to break the law for some reason. They're not going to care about breaking a second law that's already in the books there. To compare like a cold call from sort of a robot sounding voice, right, an old school robotic voice, or a completely unfamiliar or foreign voice to you versus a call with someone who sounds potentially exactly like your friend or your relative or your coworker. That's a whole different kind of level of threat, I would think. My advice to my elderly father is to not pick up the phone anymore, but he likes to pick up the phone and talk with telemarketers and scam artists and the like, so I can't seem to stop him. That's with voice, and maybe we don't pick up the phone for voice anymore, but now you get a FaceTime or something request from someone who looks exactly like someone you trust and is replicating their face, their voice, their mannerisms entirely. Again, that's not exactly possible today. Let's not bet on it not being possible tomorrow. So warn, in your case, your grandparents now that there has to be some established secondary source of trust beyond just voice, beyond just video, because that's not going to be the case going forward. That's all I wanted to cover with regards to social engineering and its relationship to machine learning. Let's leave things here for today. Thursday is MQ Bravo. I can tell we're all very excited about it. We'll jump into Internet of Things security next. It's also not really a new topic in the same sense that web application security wasn't a new topic, but we could talk more about impact of unsecured IoT devices in the context of what we've already learned. Leave it here for today. I'll see everyone on Thursday.